Good morning, everybody. I finally got my quotes all randomized, so now I don't have to like hand pick one every day. And, oh, do this one already or not? So, just run through. There'll be a new one surprise to me each morning, which bit of wisdom we'll have for the day. Here we go. A little bit of knowledge from Rafiki. Okay. Learn from your mistakes. Make the best use of that. Who all is here? Ivan is here in person, and Brian next to him. Daniela is online. Brianna is over there. Fernando is online. What's your name? Oh, there it is. Okay. Like, you know, in Zoom, it's got the preview. If your camera's not on, say your name in big text. His name was disappeared, but it's still a black box. Confused me there. All right. Then there's here. Leslie. Oh, Leslie. All right. Michelle is online. Diego is online. Naomi is over there. Lewis is right here. Natalie is online. And move. Leslie just arrived. All right, just in the nick of time, Leslie. Okay. One is here. Let's get down to business. Today we're continuing our exploration of slope. It is probably the biggest fundamental piece you will need for calculus. Everything is about, well, that's not true. When you get to integrals, it's the opposite. Okay, half of all calculus depends on slope. So I thought we would try something a little bit different. Here we go. Because there's only so many ways you can make calculating slope more involved, interesting, difficult, if you will. And a lot of those involve just different equations. And we're going to get to the different equations. So I thought we would try something else. A little bit of application. Is anyone here familiar with topographical maps? No? Excellent. This will be your chance. Right? You've probably seen them. They look something like this. Okay? So in the corner here, we have a black and white overhead view of part of the world. And then the map behind it is the topographical map that goes along with it. And the idea behind a topographical map is that it shows elevation. Because all of these contour lines divide a distance of elevation. Okay. So the whole line, if you think of it as a loop, here's a nice one because it's kind of round. So this loop all the way around indicates, looks like out here, 10. Right? Everything on that line is 10 feet above sea level. They can do this here. Go feet for this view. Okay? And then everything on the next line is 20 feet above sea level. Okay? So here's a side view where you can see these lines, just stripes across. That doesn't make for a good map. So with our overhead view map, so that we can see the area and how things relate to each other, adding these contour lines lets us also see how high up it is. So those contour lines connect points of equal elevation. So this is one way that maps can have more information. Right? You're used to different kinds of maps. You have political maps and geographical maps. This is great for if you actually want to traverse the terrain. Okay? If you ever get beyond just driving places in your car, right? Road maps are great for when you're driving. But if you're on foot, wouldn't it be really nice to know, oh, you don't want to go that way. There's a giant hill. Right? Or maybe even worse, there's a steep cliff. It doesn't show up on the map. Anybody here play Minecraft? No? None of you guys? A little bit? All right. You ever accidentally walked into a ravine? They generate ravines on the world. And from a distance, you're walking along, you just see grassland, and then grassland ahead of you, and you just go in, and all of a sudden, there's a giant hole in the world, and you fall in. You didn't see it above there. Well, if you install a mini map mod, and you can see a top-down view in the corner of your screen, right? It makes it much easier to see them. So some of these take this contour map into consideration. All right, so that's the contour lines. And then part of this will be like an element of the map key, right? Would be the contour interval. Because it's going to get really cluttered if we have to label every single line. This one's 10, this one's 20, this one's 30. Like, geez, couldn't we just set a regular interval between them and say every line is 10 more feet from the next one? That'd be really simple, right? And so that's what we do. In this case, we've got an example of Wildcat Mountain. And they tell us the interval is 20 meters. So each line represents 20 more meters above sea level than the last one. Because this is a mountain, not an island, I'm going to assume that this first line is the first contour line, and this represents 20 meters above sea level. And out here is just a flat line. So let's try and work out exactly how high the peak of Wildcat Mountain would be. The peak being the center middle point. How many contour lines do you go up? How many total meters does that climb? Fernando, are you shopping? It's your basement? Okay, well then you have a very well stocked basement then. Audio is kind of muffled, they're saying. Well, let's try. Oh, that's not let's see, microphone, volume. Zoom does not have a lot of microphone options. There's not much I can do. I guess I'll try to stay close to the mic then. And part of it might be this mask. It's a lot closer to my lips. All right, what do we got for height of the mountain? Yeah, they told us every line is 20 meters. So then, how high is the peak? You went from here to there, you got to cross 1, 2, 3, 4, 5, 6 lines. 6 times 20 is 120. 120 meters tall. Okay? So that's a nifty use of topographical maps. One possible use is they just show you the elevation. But we can do one better than that. Oh, here's another useful map tool. Instead of telling you how much every line is, they might label some of them. Every so often say, okay, this is at 700 feet. This line is 800 feet. We're going to use an even interval between them. So from 700 to 800 is 1, 2, 3, 4, 5 steps. Which means between each line is how much? 20. 20. Right? 800 minus 700, a 100-foot difference, divided by 5 intervals, 20 per interval. So that's another way you can determine that interval. Now here's where it gets interesting. These are, of course, still standard land maps, or I guess you could have a sea map. So you have a horizontal scale. So you can find a horizontal distance, and we can determine a vertical distance, right, our difference in elevation, which means we can find a slope. Right? We've got a rise, we've got a run. You can determine a slope between any 2 points on the topographical map. This is the exact same formula you're used to. And that lets us determine not only how high something is, but how steep is it going to be if I had to climb that mountain. So for example, back to Wildcat Mountain. If you wanted to get to the top, before we do the calculation, just think about this from a practical standpoint. They are suggesting a route from A to A prime. I want you to consider alternatively, you could go from here to here. Actually, let me do that in a different color. What if you took this route? It's a lot shorter, right? Well, what's the problem here? It's going to be a lot steeper, right? You're going to experience those elevation changes in quicker succession. Right? The way to interpret this topographical map is to understand that these being closer together means it's steeper and steeper. The farther apart they are, the more shallow the gradient, the easier it would be to walk up that slope or bike up that slope, right? At certain points, somewhere in here, you'd like to be looking more like a rock climbing experience, right? All right. Let's just use the A to A prime example for now. They tell us the total distance from A to A prime is half a mile. And remember the scaling they gave before. Each interval is 20 meters. Why do they have to mix units like that? I don't know. You're going to have to convert one or the other. I don't care if you convert meters to miles or miles to meters, but you want the same units on top and bottom, right? Your final slope needs to be a single number, single ratio. So you need the same units on top and bottom so that the units also cancel out. We don't want to say, oh, it's 0.7 feet per meter. That's weird. Right? Convert it to meters per meter or miles per mile and eliminate those units. Some quick reminders. Yeah, that is great. 1 mile is 5,280 feet. I don't remember feet to meters. I gotta go. 1 foot is 12 inches. 1 inch is 2.54 centimeters. And of course, 100 centimeters in a meter. Those are the ones I have memorized. Feel free to look up a different conversion if you would like. Since you are seniors, you are fully expected to make use of available tools such as calculators. Don't feel like you have to do any of this by hand, but you don't have to. Give me a thumbs up if you have an answer. Okay, use the, what's it called, reactions on Zoom. As well, there's a thumbs up option there. Now, take another minute, keep going. Natalie, do you have an answer for me? No. All right, you've got 60 seconds. Get one. Longest part here is the unit conversion. After that, it's just divide two numbers. Amanda is confused. You're looking for slope, right? Rise over run. We already determined the rise. That would be the elevation of the mountain. Going from the base of the mountain to the summit. We already said before that's 120 meters. So now we have the horizontal distance. It's half a mile. The tricky part here is you just got to convert half mile to meters. So I listed the conversions that I would use. If you have another way to, maybe you remember feet to meters. 3 point something. I don't remember what that extra something is. And then divide. Where did we get 120 meters? That was the previous question. When we last saw Wildcat Mountain, it gave us the interval of 20. We counted 6 contour intervals to the summit. So that gives us a total height of 120. So I apologize if they did not repeat that information on this new image of Wildcat Mountain, but I expect you should be able to remember one number from 5 minutes before, which it was when we started this question. Natalie, do you have a number for me?
I rounded it to 0.15.
Rounded to 0.15, 1.5?
Yeah.
Okay, so you rounded to 2 decimals? Is that what you're saying? Yeah. Okay, that's fine. It didn't specify. 2 decimals is reasonable. Okay, does that sound steep? Can we make sense of that number? Like, oh yeah, 0.15, yeah. I go on a morning jog on a 0.15 slope all the time. I have no idea what that means. I have 0 reference point. I doubt that you do, right? So the rest of this is just some practices, and we could definitely compare. Right? This one's going to have us do 2 different routes on this map. We could compare. If we had another number, right? Let's say we actually calculated this alternate route. We could choose between one. Oh, that one's definitely steeper. We would expect a bigger number, so we're going to favor the smallest one, right? But how small is small? How big is too big? How big could the slope get? What's the maximum possible slope of a line? Anyone? Zoom, maximum possible slope. You've got to be able to answer this, folks. Calculus is going to ask all kinds of questions about maximums and minimums possible. We're very interested in those extreme results. So, Brianna, wild guess. What do you think the maximum possible slope is? Ever, of any line, not just here, but like possible.
I'm going to say 1 because of the 0.15.
Ooh, I see. Yes, you're like, hey, this is a decimal, and we go up, and like maybe it's a between 0 and 1 kind of thing. That'd be really convenient because then I can convert it to a percent, right? 100% slope. That sounds good. And we'll get there in a moment. But think about any line on a graph. You calculate its slope. Could its slope be 1,000,000? This is a great way to check, by the way. If you're ever stuck with a, what's the maximum possible? Ask yourself first, is 1,000,000 allowed? Right? Just a really big positive number. Could the slope be 1,000,000? Well, that requires a rise over run. It goes up 1,000,000 points and over 1 point. Yeah, you could do that, right? You have to pick a really big scale for your graph so it fits on your paper. But you could have that. 1,000,000 is totally possible. And if 1,000,000 is possible, couldn't it just keep going? Couldn't it just get bigger and bigger? Billion, trillion, right? All the way out to infinity. Positive infinity would be the maximum possible slope. What kind of line would that be? How would you describe such a line? What do you think? What?
Vertical.
A vertical line. Yeah. This is the reason we have these vocabulary terms. We can say, oh, that's a purely vertical line. It's got, well, technically it'd be an undefined slope, right? Because the perfect vertical would have 0 run, and you can't divide by 0. But it's effectively like an infinitely sloped. Right? It's the maximum possible. So really our scale will go from 0 to positive infinity. And in any comparison, well, this is absolutely nothing compared to that. Yeah, but we can also say a slope of 1,000,000 is nothing compared to infinity, right? The analogy then breaks down. We need a better way to compare it. So I'm going to add one more step here. We're going to bring in, there's a special function that can transform the slope that goes from 0 to infinity and rein it back in and give us a percent. It will translate any slope number into a rating between 0 and 100. You want to know what it is? It's good old trigonometry tangent. I'm jumping the gun a little bit here, topically. Right? We'll talk more about trig in the future. But if you remember your right triangle trig, SOHCAHTOA, tangent is opposite over adjacent, right? Are you visual people out there? Here's a slope. Oh, I can always look at it as a right triangle. The opposite side is the rise. The adjacent side is my run. Opposite over adjacent, rise over run. It's the same thing, right? So I'm tangent of the slope. Tangent of the angle gets us back to that slope, right? So we already have the slope, and we would rather have a between 0 and 90. Right? Wouldn't that tell us how steep the thing is? 90 would be the most steepest ever, literally impossible. 0 degrees, totally flat land. Wouldn't that be a much easier comparison? We can visualize that in our head. Oh, okay, so this is 10 degrees. It's a 60-degree slope, right? Now that has meaning. So this number goes here. That is our slope. So we want to reverse that. Take the inverse tangent of 0.15. What do you get? Yeah.
8.53.
And you're in degree level? Okay, yeah, okay. 8.53 degrees. So it's about like that. Right? That's not much. But now we have a better feel. We have something to compare to. Right? We can picture that as somewhere between 0 and 90. Right? So that's a much more intuitive number, in my opinion. That's one of the beautiful things about trigonometry. Right? We can do fancy things like that. Okay. Questions on how to find the slope on the topographic line? Remaining questions on how to get this 0.15 number. No? All right, then next page. First practice. And folks here, I recommend go ahead and take out your Chromebook and open up the document yourself, better view there. Rather than trying to count the little lines on my screen up here. So this map has the scale there on the bottom left. That much is 0.2 miles. And tells us the contour interval. Contour should be a U there. And yeah, you're going to have to figure out a way to measure between those points. This is the real life problem, right? Not every distance on the map is pre-measured out for you. This is why some of the good navigational compasses have a little ruler on the edge. So you can actually measure on the map. Okay, well, it's 3 inches across here, and the scale is 1 inch is a mile, and so. Right? So, whatever screen, just don't adjust your zoom view as you do it. Measure out, okay, this is a thumb width, and so it's 3.5 thumbs, or whatever you got to use. Find the distance between the points, count the number of contour lines, multiply by the interval, divide those values. There was, yeah, now on the last page there is one more. Same deal. So 2 practice maps, 4 routes. We've got 5 minutes left to work on that. These ones, thankfully, at least are in feet and miles, so the units are all in the same system. Should go much faster. When you have your answers, please go ahead and upload them to the Google Classroom assignment. Either type them up or just take a picture of your handwritten work. That would be easier. And reminder, please have read and taken notes for the linear equations section by tomorrow. Not a separate due date, part of that full homework of the week due Friday. But I'd like us to all be on the same page there tomorrow. Okay? And with that, we'll end the YouTube stream.